Test. All right, good, thank you. All right, good evening. Let's get started. So today we're going to learn a new type of technique in terms of computing the double integrals. And this is called change of variables. So let's take a look at together. What is this change of variables? Give me a second here. Let me turn on the. Good. So. First of all, the idea of a change of variables is not actually new, right? We have seen the examples of change of variables. You know, in polar coordinates, right? You have x equal to r cosine theta and y equal to r sine theta. Okay. So this is a change of variable. So what's changed? You change from x to r theta, and then y also changed to r theta, right? So basically your x is a function of r and theta, and y is a function of r theta. So that's what we already seen. But now let's look at not just necessarily from Cartesian to polar. Let's look at the general concept of change of variables. Okay. So general concept basically means in general, okay, your x and y, okay, you wanted to change to a new pair of variables u and v. So basically you want to come up with a function just like this one here, x equal to r cosine theta. You want to come up with a function so the x is a function of the new pair of variable u and v, and y is another function of u and v. Okay, so this is a general idea of a change of variable. So if I have to see this, essentially you have u, v at here, and you also have x and y at here. Okay, so technically, they're interchangeable. You could transform from here to there, or you transform back from x, y to u and v. Right? So that's called the change of variable here. Now, this is important. Okay, this part of information is important because you do need an expression relating your x, y, and u and v together. So now what we can do is, okay, we can define a so-called coordinate transformation vector function.
So let's define a new function. It's called a coordinate transformation, okay, vector function. And this function defined as t, okay, which is a vector equal to x u of v and y u of v. So it's directly created, okay, it is created based on your function x and y. Okay. So remember, this is a given. You're already either given or you define yourself, right? So that's something you have to have in order to create this coordinate transformation vector function. Okay, yeah. So what does this so-called coordinate transformation function do? I mean, first of all, you need to understand why it is called a coordinate transformation, because you have a coordinates x, y, you also have a coordinates u and v. So what this vector function does is establish the connection between x, y, and u and v. Okay, so that's why it is called coordinate transformation, right? So technically, right? So what it does is, let's say this is your UV coordinate system, right? And then you may actually have certain region, let's call it R prime, okay, in the UV coordinate system. Okay. So the region could be anything, you know, could be maybe just a rectangle, a circle, or it could be a triangle, right? Could be any type of region. And then because you have established a coordinate transformation vector function, like giving it here. Okay, so established means whatever that you created, however you created this coordinate transformation vector. Okay. Then basically this vector here, okay, you can apply this coordinate vector to this region R, right? Which means basically you pick any value, you pick any coordinates UV from this region, you plug in into here, right? And then you have the function, then you'll be able to get a value for x and y. So what this does is, it basically, you can transform this region R prime in the UV coordinate system into some sort of a new region, okay? So I'm just, without specifying, we have the function here. So you can transform this R prime into here, okay? Let's call this as R here. So this red color, read R prime. Okay, I'm just arbitrary drawing here. Maybe it's transformed to a different geometry or different shape. Let's call it R this time, right? So this coordinate transformation vector function, it does some sort of a scaling, okay, twisting or rotating, okay. You know, however, that's decided by the vector by the function given at here. Okay. So you will be able to transform this geometry into this kind of a shape, okay, from R prime to this. And that's what this T at here does. Okay. So the usage is very actually good, because the idea is, for example, if you have a very sophisticated geometry in the UV prime, and then you actually can maybe transform into another coordinate system, okay, which becomes simpler. And that's very true, right? So that's called a changing of perspective. And this is actually quite important, even as a life, as a philosophy of your life, you know, you have to change your perspective, right? And when you change your perspective, then the whole problem will look quite different. Okay. So that's what we're going to do here. How can we change the perspective? How does that help with this computation of a double integral? Okay. So let's go back to this coordinate transformation vector function at here. Now, once you have this vector function defined, right? So this T at here, so basically this T here is a function of X, it's a function of U and V, right? Yeah, because X is function U and V, Y is functions, and this one is also function U and V. So this next one is you must have seen this, right? From your previous, from your other classes, is that once you have this function here, you can create the so-called Jacobian matrix. Okay, so the Jacobian matrix is constructed based on this vector function right here. The first function within this vector is x. The second function within the vector is y. Okay. So you can technically Jacobian matrix, you can have as many functions as possible. You can have any number of functions, but here we only have 2. Okay. So the Jacobian matrix is use the first function here, partial x, and over partial u, and then partial x, partial v. So the first row, right? The first row is essentially the gradient, right? The gradient of this first function x. And the second row is, right, is constructed by the partial derivative, okay, of the second function over here. Right? So that's your second row. Yes. So this is called a column vector. Okay? And the vector itself consists of n number of functions. In this case, we only have 2 functions here, right? It's a column vector of 2 functions. And then Jacobian is constructed, right? Exactly, you don't change anything, exactly based on the 2 functions. First row is a gradient of the first function. Second row is a gradient vector of the second function. Okay. So once we get this Jacobian matrix, okay, and then the next important thing we can immediately calculate the Jacobian matrix is the determinant of this Jacobian matrix. So let's call this as a J. Call this is a J at here. The determinants, right? That's basically calculate the determinant of the 2x2 matrix. That's simple enough, right? And then to determine a 2x2 matrix is this term times this term minus this term times this term. Okay. So the notation wise, we denote, okay, we denote this 2x2 determinant as using this notation. So this notation basically represents the determinant of the Jacobian matrix. So, and this is also called, sometimes called the Jacobian. So the determinant Jacobian is shortened as so-called the Jacobian. It's a very important quantity to have. Okay. So without, then the next one, I'm going to write on a conclusion, but we're not going to write any proof. Okay, the proof itself will be quite a bit of a lengthy process. So then, the general change of variables theorem. Okay, so this theorem states here is your original double integral, which is in terms of x, y, Cartesian coordinates. Then I can transform this into a computation in terms of u and v. So x at here, you can replace with the function x u of v, and y can also be replaced with that function y of u and v. The dA, okay, which is originally dx dy, or dy dx, and now will be du dv. However, okay, you got to insert a term at here, which is this absolute value of the determinants of the Jacobian. So this is basically the change of the variable theorem here. You're changing from x, y to u and v. So you look at the formula here. Now you can let it sink in what's involved at here, right? You need to calculate, you need to find the relationship between x and uv, and also the relationship between y and u and v. You also need to calculate the determinant of the Jacobian. Of course, you have to construct the Jacobian first, and then you can calculate the determinant. Right? And you plug it here, and don't forget the absolute sign at here. So basically, absolute value, okay? And then you can calculate. So this is r prime. Okay, so from r, so the original region is r, and then the new region is actually r prime. Okay, the geometry often in time will be looking different. Okay, so that's the principle we're going to stick to. We'll look at some examples how to properly use this change of variable theorem. Okay, but first, let's look at an example of a change of variable. Okay, let's consider that polar coordinates. This is the change of variable example, which we have already used for calculating this double integral. And if you recall that when you change this from Cartesian to polar, right? Do you remember your dA? Instead of a dA, you have a dr d theta. And do you remember this? There's r at here, right? So there's r in front of dr d theta. So I want to demonstrate basically is where this r is from, right? Basically, you can see the r needs to come from this determinant of the Jacobian, okay, the absolute value of that. Okay. So let's see if we can actually use the current formula to derive this r, right? To give us this r here. So first, construct the Jacobian based on the two given functions at here. So your Jacobian formula is partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta. And the reason is you're not using uv anymore, right? So because your u and v here is basically your r and theta. Okay. So then you have your x and y expression. So calculate the partial derivatives. Partial x, partial r, cosine theta. Partial x, partial theta, negative r, sine theta. Partial y, partial r, sine theta. And partial y, partial theta is r cosine theta. And so then calculate, next step, calculate the determinant of the Jacobian. Determinant Jacobian is this term, multiply this term, then minus, right, the other multiplication of the other term. So you got r cosine theta square minus, okay, and it's a negative r sine theta square. So negative negative become positive. So you got r cosine theta square plus r sine theta square. Common factor is r, and you're left with cosine theta square plus sine theta square, which is 1. So that's just equal to r. Okay. So that's where your r is from. Now you might wonder, isn't that you have an absolute value of this determinant of the Jacobian, right? Yes. So the absolute value basically is to ensure that you need to put a positive value at here. And if you recall, the definition of r is the distance from origin to anywhere of the location of the coordinates of the points. So that's naturally, it's a value greater than 0, right? So you don't need any absolute sign at all, right? So that's basically a proof of how the polar coordinates transformation, right? How the r is obtained. Okay. So as you can clearly see, the key is obtain the relationship between X and your U and V, or R theta in this case, and then obtain the relationship between your Y and the other ones, right? And then Jacobian and determine Jacobian. Okay. Now let's look at an example here. So let's consider this particular region R. And region R is defined by this relationship right here. 2x minus 1 greater than 1 less than 3, x plus y greater than -2 and less than 0. Okay. And let's integrate this double integral. Okay. So it's always good to be able to sketch the region R right here. Now, if you don't have a computer, sometimes sketch could be a little bit trickier. But in your head, you can always try to visualize what's going on here, right? So what's going on, basically you have 2x minus y less than 3 or greater than 1. Now, if you just focus on the equal sign here, then 2x minus 1 equal to 1 or 2x minus 1 equal to 3, or at the bottom here equal to -2, the bottom here equal to 0. So then you get essentially a straight line, right, for each one of the equal sign. Okay, so you got 4 straight lines here. In your head, in your 2D, you got 4 straight lines. And then the greater or the less signs basically means it's either on the top of the straight line or at the bottom of the straight line, right? So the 4 straight lines at the bottom, at the bottom or at the top. So when you put them together, then you get a certain region, right, sandwiched by the 4 lines. Okay, so that's essentially what R will give it to you. So to save myself a little bit of time here, and basically this is your region R, which is like a parallelogram here, right, a diamond. Right? So I'm gonna just paste it over here. Okay. And the idea is to integrate this double integral. Now you certainly actually have more than one method to do this. You can actually once we finish this, I will teach you another approach. Is that you can integrate by parts. So you have by pieces. Okay, you can separate this region R into 2 pieces. Okay, and then you integrate over this piece and over another piece, right, separately. Okay, yeah. But bottom line is, okay, this is not the typical type of region that you prefer to work with. You really probably like to work with a regular rectangle, right, which give you very simple integral limits. Okay, so in this case, this change of variable is a perfect approach to apply to this type of question at here. And even change of variable, you do not have actually the only solution. You could change your variables slightly differently. Okay, so here's what we're gonna do. We're gonna introduce, sorry, this is your x, y at here. So we're gonna introduce a set of new variables. So we're gonna let u, okay, equal to 2x minus y, and v equal to x plus y. So I'm introducing a new set of coordinates, u and v. Okay. And the reason we're trying to introduce this u and v at here, you can immediately actually see a benefit. So if I give you a region R in terms of u and v, let's say you put a u here, you put a v at here. Okay. And guess what? Now you have u greater than 1, less than 3, v greater than -2, and less than 0. And that's a very regular box, right? Rectangle, okay? And that's the geometry you typically would prefer to work with. Okay? So that's the background here, why you want to introduce the UV like this. Okay? So then next step, right, is you want to apply this change of variable theorem. Then you look at the theorem here, then I need to obtain, right? I need to obtain a relationship between x and u and v. So you need to obtain an expression for x in terms of the newly introduced coordinates, u and v, right? And same thing for the y. But I don't have it right now, right? All I have is the two relationships here. So the next step, what you need to do is you need to solve for x and y, okay? And to get an expression for both of them in terms of u and v. And that's what we need to do next. So for now, you need to consider u and v as if they are some sort of a constant. You keep it, just keep it there, right? Essentially, you got a set of linear equations, and you try to solve for x and y in terms of u and v here. So let's take a look at how you can solve it. So, for example, right? If this is your equation 1, equation 2, so you add the two equations, okay? Then your negative y and positive y will cancel each other. So you get u plus v equal to 3x. So then x equal to 1/3 u plus v. Right, so that gives you, right, this is basically a function of u and v. Right? And that's what we're looking for. And similarly, you can try to get a solution for y. So what I could do is, so this is 2x, this is x. So if I use 1 minus 2 times 2. Okay. So 2 times 2, you got a 2x, then y minus 2, the 2x will cancel, then you get a solution for the y, right? So if you do that, so you get a u minus 2v equal to negative 3y. Okay. So that gives you a y, right? Negative, you can change the direction there, so 1/3, so 2v minus u. Okay. Or write u at the front, so u minus, negative u plus 2v. Right? It's the same thing. Okay. So now you get, let me rewrite it here. So you have a function for x in terms of u and v, which is 1/3 u plus v. You also have a function for y, and that's 1/3 negative u plus 2v. Okay. And the region, right? The region, if I had to sketch that, so this is in the UV coordinate system. So according to the transformation, instead of 2x minus y greater than 1 less than 3, and you have u greater than 1 less than 3, and v greater than negative 2 less than 0. So if I had to sketch this, that's much simple, right? So u is between 1 and 3, and v is between negative 2 and 0. So obviously, right, the region, okay, will look like this now with the introduction of the u and v pair of new coordinates. Okay. And this is a much simpler region to work with. So if this is R, right, this is your R prime. Okay. 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 So the next few steps will be strictly follow the formulas for the change of variable theorem. So you construct your Jacobian. Also typically just directly from the formula. So let's see what's the Jacobian here. Calculate partial derivative, partial x, partial u, 1/3. Partial x, partial v is also 1/3. Partial y, partial u, negative 1/3. Partial y, partial v, 2/3. So 1/3 times 2/3 minus of the negative of 1/3 times 1/3. So that's what do I get? So 2 9s plus 1 9s, so 3 9s. I get it 1/3. So this is the value of the Jacob. Sorry, I think I'm jumping ahead of myself at here. This is Jacobian, right? So what's next? Then determinant of Jacobian is 1/3. Okay. And this is the value that we're going to put it into the change of variable formula. So your original integral is this. And now, okay, you're integrating, okay, instead of integrating x and y, you're integrating using u and v. X out of here, what do I do with the x? X will be replaced with the expression that you have find out, 1/3 u plus v. And then du dv, plugging this 1/3, you have just find out based on the determinant of the Jacobian. Okay. So that's it. That's completely transform everything from x, y into u and v. So the next step is to find the limits for u and v, right, based on the new region, R prime. And new region, as I draw here, is like this. It's a rectangle. So the limits is quite straightforward. So let's do a little bit of simplification. So you get a 1/3 here, u plus v. So let's say I integrate du dv as the order. So the u goes from 1 to 3, v goes from -2 to 0. Right? And you look at this integral right here. This is very simple to integrate, right? There's nothing tricky. You get a 4 at here. So you can immediately see the benefit, right, of this integral by parts. Sorry, the change of variable. Right? Yeah. Okay. So the general idea when you look at the change of variable is you have to find a replacement, right? This one is actually quite straightforward. Yeah, your replacements, right, is u equal to this, v equal to that. Now, I will give you an example next. Okay? Some other ones, you do have a different options to do the replacement. Okay, so I'll show you an example next. So I'm going to temporarily goes away from this change of variable to give you another constant, then we'll come back to the change of variable again, okay, to show you another example. So any questions so far about the change of variable? So yeah, it's quite clear, right? I think you look at the process here, it does need a little bit to practice at the beginning. The keys is to define the u and the v, okay? So one thing I want to cover, which is the last part of double integral, is what are some of the properties of a double integral. So property double integral, very much like integrations of single variables that are here, right? So I'm not going to write all of them here. Some of them are just purely, straightforward. For example, if you multiply constant with the function you're integrating a constant, you can always take the constant out of the integral, right? So this is same as function single variables. If you're adding two functions and then do the integral, you can always separate the integral into two pieces, two parts, okay, which is basically same as single variable. Okay. Another one is, okay, if your function you're integrating is more than 0, then the whole double integral will also be more than 0. Okay, so this one here, maybe I can elaborate a little bit. Okay, so this property. So I'll give you a very illustrative concept of why when this function is more than 0, then the double integral is more than 0, right? So for the first one right here, so this is how, remember this is how we approach double integral. We approach double integral, say, if I have a function f of x, y, and here I have a region here, then we say, what is the volume, right? What is the volume below this surface and on top of the region R? And that's how we approach this double integral at the beginning. And you end up with basically this double integral. Okay, so the volume below this surface and above R is given by the double integral. So now you can clearly see if the double integral is more than 0, basically means all of the values on the surface is on top of the xy plane. Then the volume below this surface and above region R is guaranteed to be more than 0, right? You have a positive volume basically. Okay. So that's why, right, this property holds. Okay. The second property is that if this value is more, this function is more than the other function over region R, then this double integral is more than the other double integral. Same meaning, you can interpret it. So if this function is more than and the other function, okay, then the volume, right, created between this function f and r will definitely be more than the volume created between the function g and r. Okay, so that's why this property holds. Okay, okay, so the other property, which is what I want to spend a little bit more time is additive property. Okay, so it's additive property. So let's look at this additive property. The additive property essentially is the analogy of integral by pieces in function single variables. So let's say suppose when you have a region R, your R consists of multiple small regions. Okay, let's just use two regions to illustrate. Then what the property basically says is, if you're integrating this function over region R, then you can integrate over each one of the small regions and then add them together. Okay. Right, so this is in energy, for example. If you have a curve from A to B, then B to C, and this is your function f. So remember what you do, you can integrate from A to B, then integrate from B to C. Right? That's the same analogy there. So let's take a look at an example of how we can make use of this additive property. Okay, under what situations you use this additive property. So R is defined by y equal to 2x, y equal to 1/2 x, x plus y equal to 2. Okay, so this one is easy to sketch because all of them are just straight lines. Y equal to 2x has a slope of 2. Y equal to 1/2 x has a slope of 1/2. And then x plus y equal to 2. It has a geometry like this. This is 2 here, this is 2 here, and this is y, x plus y equal to 2. So the three things construct together give you this triangle at here. So this is your region R. So let's suppose you are required to integrate certain function, okay, without specifying the function at here. So you want to calculate this double integral. Okay, so let's try the very traditional approach. Right? Cartesian coordinate, you got a region R. Right. First step, determine the order of integration. So let's say dy dx. Second step is to determine the limits for y and the limits for the x, right? So how do we do that? Remember, right? So what we do is we draw an arrow line, okay, in the positive y-axis direction to find the y mean and the y max. Okay? So in this case, the y mean is right here, the y max is right here. However, you see the problem? If I draw it over here, then the y mean is here and the y max is here. So when I draw it at a different location, my y max is actually different. So that basically will promote you to think differently. Okay, I probably will have to separate the region into two pieces. So you can draw a vertical line right in the middle. Then you have this region, you can call this R1. And you have another one here, you can call this as R2. All you have to do is integrate over R1 and R2 separately, then add them together to give you the result of the double integral. Okay, yeah. So let's try that. So the key I want to demonstrate is to show you how to find the limits, basically. Okay, so let's see, now we're integrating over R1 and R2. So let's look at the integration over R1 first. And what will be the limits for region R1? Same approach. Okay, so you know where region R1 is this triangle here. So this is the arrow lines that we have drawn. And first contact give you y mean. So y mean is on this line here. So that's 1 over 2x. Second contact falls onto this line here. So that's 2x. Right, that's y mean and y max. X mean is you sweep this arrow line from one end to the other end. So one edge to the other edge. So the two edges, right? One is over here and then one right in the middle, right? That's edge. And that's how you find the x mean and x max. Obviously, x mean is 0. And the x max is right here. So the x max can be decided based on the coordinates of this point. Right, so now you see, let's take a look at them. What is a coordinate? Let's call this is coordinate. This is point A. This is point B. Right, so we have to find the coordinates for point A and B. So for point A, okay, point A is the intersection between y equal to 2x and x plus y equal to 2. Right, that's the coordinate. Point A can be decided based on the intersection of the two lines. So you got two equations, two variables, and you can solve for the x and y. So you get the coordinate A is 2 over 3 and 4 over 3. X is 2 over 3. So your x max, right, for the R1 region is 2 over 3. So once you have, if you have the function f, then you can carry on with the rest of the integrals. Similarly for R2, So for R2, what you're doing is you draw an arrow line in the positive x direction. First contact, y mean, which is 1/2 x. Second contact falls onto this line here. That's y equal to 2 minus x. So y mean and y max based on the R2 region, right? This region here. Right? Then the next step, you sweep this arrow line from one edge to the other edge to get the x mean and x max. So x mean is the coordinates for the point A. X coordinates for the point A, and that's 2/3. And x max is determined by the coordinates of point B, right? So then let's do the coordinate point B here. So for B, it's the intersection between y equal to 1/2 x and y plus x equal to 2. That gives you the coordinate B and 4/3 to, okay, and y is 2/3. So your x max is 4/3, right, based on this value. This is essentially the additive property. When you add, when you have the function, you do each one of the integral, you add them up, and you get a total. Okay, whatever the results is. Okay, yeah, additive property. Okay. So nothing really different from a traditional double integral, right? Except that you just sort of separate your region R into 2 or even more little regions, right, for you to integrate over. Okay. So I still have 5 minutes, but I wanted to give you a different perspective. How about the change of variable concept or technique? Okay. Can we apply the change of variable technique to this question at here? So because you can clearly see this triangle here, right? Give you a little bit of trouble because you had to separate into 2 regions and then you do it. So what if I could use change of variable so that I don't have to use the additive property? I could just get it done in one shot, right? So here's what we can do. So I'm gonna let u equal to x plus y, okay? So basically what I'm doing is, you see this edge here, this boundary, x plus y equal to 2. I'm replacing it with u equal to 2. Okay, so this is what I'm done, u equal to x plus y. And then I can also define another one, v equal to y minus 2x. So what there to come from is, it comes from this line here, right? So this line basically is y minus 2x equal to 0. So I'm defining v as y minus 2x. Okay. So what's the advantage of this is, if your u is x plus y, v is this. So technically what you're getting here is, according to your original expression, u equal to 2 and v equal to, what's v? Now, if this is your definition of v, the v must be 0, exactly, right? V must be 0. Okay, so then think about it. If I need to construct this region R in the UV coordinate system, so your original boundary x plus y equal to 2 becomes u equal to 2. Where's u equal to 2? U equal to 2, this is 1, this is 2. So u equal to 2, right? This is a u equal to 2. Your original boundary y equal to 2x in the UV system becomes v equal to 0. V equal to 0, what is v equal to 0? Yes. What is v equal to 0 in the UV system? That's just a straight line on the u-axis. That's basically just u-axis, right? Yeah. So this is your v equal to 0. Okay, so you already have 2 boundaries at here. Okay? You just need the third boundary. Basically, what happened to the other one here, this one, right? How is that going to be transformed here? So we need to do a little bit of computation, right? You can clearly see there used to be a wicked geometry, now actually becoming a little bit more straight, right? Yeah. So here's your definition U and V. If I need to apply the change of variable technique, what I need to do is I need to solve for X and Y based on these two given expressions, very much like what we did in the previous example. You can solve for X and Y, you get X equal to 1/3 U minus V, and Y equal to 1/3 2U plus V. Just solve it like a set of linear equations. All right, so once you get X and Y, remember the third boundary, right? The third boundary is Y equal to 1/2 X. So Y equal to 1/2 X. So I can substitute Y with 1/3 2U plus V and substitute X with 1/3 U minus V. Okay. And then I can simplify to get an expression relating U and V at here. So that gives you U plus V equal to 0 if you simplify this expression. So basically means your original boundary Y equal to 1/3 or 1/2 X transformed to U plus V equal to 0, and which is this line. So now you see, this is the new region R, right? Based on this introduction of the new variables. Okay, so I can finish, I'm going to finish the example in the next lecture, right? Is to apply the Jacobian, right? And to carry out this change of variables. But the rest of the things is actually quite straightforward. Okay. Okay, any questions? All good? Okay. So yeah, feel free to come over here if you have any questions. Otherwise, well, I guess have a good weekend.